Tell me when.
Yeah, go ahead.
Okay, folks, as you guys know, I'm going to be on Kairos. Actually, I am on Kairos. You guys are there. So, a few things to remember. One is that remember we're going to have the next class, we're going to be finishing up the practicals that we've got. So if you haven't gone, make sure that you're cool with that. The whole aspect of this particular section that we're coming up to now is this whole section of using electrical energy. Okay? So one of the huge concepts that we have is power. And we know, I'm going to put these here because we're going to be using them. Power is I squared R. Power is IV. Power is V squared over R. Remember this. So with power, you sit there and say IV because it's the current, and then the amount of charge which is available, and that's going to be getting you the power that you've got. Okay? I've got the R there for that. So, we're going to start going over these. We're going to do it just like we did before, which was, we're going to do a section, then we're going to pause it for a little bit, then we'll do the next section, pause for a little bit. So, let's start with this then. This is the note taker you guys had before. I'm going to go over this super fast. So, with this, a car engine drives a generator which transfers energy to the car battery. Headlights use the energy stored in the car battery to produce light. List the forms of energy in these three operations. Okay, so a car engine drives a generator. So what you've got is that the wheels which turn around, that mechanical energy is then turned into electrical energy. In a battery, you've got chemical energy which goes into electric energy. And then with the headlight, you get electric energy which goes into light and heat and those sorts of things. Thermal energy is going to become important for us, the heat. The next one down here, this is one I think is actually important. Hair dryer operating 120 volts has two settings, hot and warm. In which setting is the resistance most likely to be smaller and why? Well, remember, if you want it to be hot, you're going to want to have a lot of electrons going through. If you want a lot of electrons going through, small resistance. And so therefore, that's why you want the setting to be small resistance if you're going to be getting more heat and more power associated with it. A couple of other real quick things just for you guys to know. Do electric companies deliver energy or power? You should realize that they're delivering energy. That's what you're taking a look at. And in fact, the value that we use is the kilowatt hour. Remember, kilowatts, which is the power is energy over time. And so you sit there and go, okay, well, kilowatts, that's going to be energy over time. Hours is time. Those cancel. Energy, you get joules. Okay? So realize and appreciate that. Which household delivers devices require more than 1,000 watts of power? These are going to be the guys that really are gaining a lot. If you got to do a lot of power, that's going to be water heaters, clothes dryers, microwave ovens, heaters, stoves, those sorts of things. They're going to have 1,000 watts of power. Anything that needs a lot. And then why would an electric range, an electric hot water heater be connected to a 240 volt circuit rather than 120? Ranges and hot water heaters require a tremendous amount of energy. And because they require a tremendous amount of energy, I need a big old dam. And that's why the 240 is going to be better there for you. More power you're going to be able to generate. Remember, power itself is V squared over R. It's also VI. So if you've got this greater voltage, you're going to get the greater power to do these things which take a lot of energy. All right. With that, we're going to get into the worksheet. So, the first one, you guys should be pretty cool with this. You should be able to use these equations to get what you need. Remember, we've got the power equations here. We have the power with energy, which happens to be right there. So, I'm going to let you guys go on this one. Now we're going to take a little break and start up again. So, for right now, for the sub, please turn it off. Okay. So now, hopefully you guys have had some time to look at this. Let's go through the whole kit and caboodle, okay? So, first thing, you want to draw a circuit. 120 volts, boom. Make sure you've got your battery, positive, negative, coming up. You've got a 15 ohm resistor. This guy's going to come back through there. It's going to go, okay, so there's your circuit. Now I need the current. Well, I only have one resistor, so I can do that. I take a look at my equation, V equals IR. I want the current, so I'm going to go I equals V over R. So I'm going to take my 120 volts and put it over the 15 ohms. And what you should have found on that particular one, I'm going to use my little cheat sheet here, you should have gotten 8 amps. A massive amount. So now I've got my current. It says power. Look at your power equations. And there's a variety of ways that we can go. I'm going to choose power equals IV. I know that's 8 amps. And I know the voltage here is 120 volts. So when you do that, you should find out it's going to be 960 watts. You can also go and use these other equations. If you've got the information, you can use any of these and it should work out. So for example, I could have gotten P equals V squared over the R. And in that case, it would be 120 volts squared divided by the 15 ohms. And once again, you're going to get the 960 watts. So it doesn't matter which way you go. Now I want to use energy. And I need my energy equation. Power is energy over time. You got your time there. Power, energy over time. I want to know how much energy multiplied by the time. Power times time is energy. So you go 960 watts, 30 seconds, bingo, bango, boongo, and you're going to get 29,000 joules. Remember, energy is joules. This is a water heater. And so you're saying, so how much thermal energy is liberated? Same amount. It's the same sort of stuff. Okay? So, get your circuit, figure current, use your power. From the power, you can get the energy, and you can see what's going on. All right. Now we're going to have you guys do the next one. So this is going to be number 2. Set it up, do it. I'll be back in a second. Okay, you guys are back. I'm erasing. So here we go. Here's number 2. This one. 39 ohm resistor, 45 volt battery. Folks, write it each time. Positive, negative, coming through. 39 ohm resistor. Coming back through like so. It wants to know the current. Well, that means that you go current is V over R. No problem. 45 volts, 39 ohms. You sit there and you find out on this one it's 1.15 amps, or 1.2. And then it says how much energy is used by the resistor in 5 minutes. This problem actually is a little tricky. Why? I want energy. So you sit there and go, power is energy over time. Okay, I'm going to isolate it. Energy equals power times time. And you go, cool, I've got the time, I've got the 5 minutes. Time is 5 minutes. Don't forget, you have to have it. A minute is 60 seconds because you've got to be in seconds. 300 seconds. So you go, cool, there's my 300 seconds. But, what's my problem? I don't have power. So I've got to have power. How do I get power? That's when I come back to these equations here. So I can sit there and go, hey, power is IV or VI, whichever you want to say it. And I do have the current, 1.15 amps. I do have the voltage, 45 volt battery. So now I can sit there and do that, and I find out that I've got 54 watts. Remember, what are we? We're physics rappers. Why? Because we break it down. And why? Because we know Carter, the guy who's actually taking this right now, rap star just by himself. We call him King C. Okay, now, or Mr. Carter. Now, with this then, this guy is going to come into here. So it's going to be 54 watts. Now you just multiply that out, and you get 16,200 joules. So far, so bad? Good. All right, head on to, you know what, 3 isn't too bad. I think you guys can get that one pretty easily. I'll let you guys work and do that one. Let's do 4, okay? We're going to take a quick look at 4. So, I'm going to erase this, get this together. While you're doing that, sub, if you could go and stop it again to get these guys time so they can go and work on the next one, that would be great. All right. So you folks are back. Nice to see you. All right, let's see what we've got. Let me get this guy down just a little bit. Whoop. All right. A bulb powered by a 120 volt source, okay? Voltage, 120 volts. Resistance, 5 ohms, okay? At room temperature. So this is at room temperature. And it's 100 ohms when it's at operating temperature. So I'm going to call that O. R is going to be room temperature. O is going to be operating temperature. Now it says, what's the current when the bulb is turned on at room temperature? All right, just to take a look, just real quick, because we always want to have this. That's 120 volts, that's your voltage. And now it's going through a resistor. But this resistor changes. Turns out when you heat a resistor up, the resistance goes down. And so you've got a situation like this in this particular case, okay? So, I'm sorry, when the temperature goes up, the resistance goes up. Sorry, my bad on that one. Temperature up, resistance up, because the particles move faster, it's harder for the electrons to get through. That's why if you're using superconductors, they really get it down to close to freezing, way past freezing, liquid nitrogen sort of temperatures. At any rate, what's the current when the bulb is at room temperature? Well, that means you're going to use this guy. I equals V over R. You go V is 120 volts, R is 5 ohms. You can sit there and do that pretty easily and find out that we've got 24 amps. Now it says, what's the power? Go back to this equation. Power equals IV. 24 amps, 120 volts. And the power that you're going to generate on this guy is going to be 2,900 watts. Now remember, you could do this IV, you could do this I squared R. There's all sorts of ways that you can do this. All of them valid. Now it says, what's the current when the bulb is at operating temperature? Well, we sit there and say, okay, it's now going to be 120 volts, but now the resistance, as we see, is 100 ohms. Now this particular point, you get 1.2 amps. Notice that my resistance went up, so my current goes down, just like we'd expect. Now the power, if I've got less current, less power. So I go, okay, power once again, I can do I squared R, I can do VI, I'm going to do VI in this case. I'm going to go to 120 volts by 1.2 amps. And when you do this, you get 144 watts. Boom. So you guys should be cool with that. And once again, 5, I don't think much of a problem. Now though, I want to go to a cool problem that we have set up. It's called the Tesla problem, charging a Tesla. Let's take a look at this one. As we're aware, electric cars are making a bigger and bigger impact in our country and in the world. Now, an interesting thing about that is, I have to mention, while electric cars are really awesome and they do really, really great things, one thing about electric cars is you've got to get the electricity. So are they truly zero emission? Not really. Depends where you get your power from. Where do you get the electricity from to run it? Okay? And the real technology that's important is the battery. So with this, let's start bouncing through this guy. Couple things we need to know. First thing, familiar with the idea of potential energy? Water is a usable source of stored energy. This is hydroelectric energy. How does it basically work? And we're going to be seeing videos in just a little bit. Hydroelectric energy. Remember, there's going to be a wire. There's going to be a magnet. We talked about this before. North-south. When it rotates, it takes the electrons in the wire and makes it move out one direction, and then as it rotates the other side, move back the other way. You get an alternating current which is going. The big thing is, how do you turn the magnet? That's a turbine. We can turn turbines with oil or coal or gasoline that we go and we make steam, and then it can turn it there. We can take hydroelectric power as it comes down the dam, turns the turbine. We can take a windmill, turn it, and that'll turn the turbine. Obviously, wind and hydroelectric, these particular ones, have the advantage of not having to burn fossil fuels for it. So therefore, that truly is a zero emission sort of thing. If you're talking about oil or coal or gas, totally different story. So, two types of batteries. First thing I want to know is, what is the potential energy of the 70 kilowatt hour Tesla. Remember, kilowatt hours is actually an energy. So you go 70 kilowatt hours. First thing I got to do, turn it to kilowatts. 1 kilowatt, 1,000 watts. And then it's an hour. So I'm going to put an hour down here. That hour, 3,600 seconds. So that means the potential energy that this battery can actually attain is 2.52 times 10 to the 8th joules. An amazing amount. Okay? Battery technology, by the way, is the thing of the future. That's what you're really taking a look at. All right. Take a second. We're going to turn this off just for a second. It says, keep in mind the efficiency of many turbines is only 50%. So what's the potential energy of water required to produce the energy of the battery? So turn it off just for a second, and then we'll come back and see what it looks like. All right, let's take a look at what we got. It's only 50% efficient. So I don't need 2.52 times 10 to the 8th joules. Because it's only 50%, I need to multiply that by 2. And so therefore, when I do that, I get 5.04 times 10 to the 8th joules. Efficiency, very important. The more efficient you get, the better you're going to be. Most things that we have really aren't that terribly efficient. Then it says, at Hoover Dam, the water falls 150 meters to drive the turbine. Okay, so here's the water. The distance that you're talking about is 150 meters. Okay, we'll call that the height. So 150 meters is the height. We know the G, 9.8 meters per second squared. And we know potential energy is mgh. We know that from stuff we've done before. And we know the energy that I need for the battery, the potential energy I need, is that number there. All right, let's take a break real quick. You guys go in, figure it out. We'll come right back. So Sub, if you could turn it off just for a second. All right, you guys figure it out? I need to solve for mass. So I'm going to go potential energy divided by GH. That's going to be your mass. So 5.404 times 10 to the 8th joules divided by 9.8 meters per second squared, okay, times the height, which is 150 meters. To charge 1 Tesla, you are going to need 90,583 gallons. Okay? And I think this should be joules there. Sorry about not having the joules. Okay? So, the mass that you're going to be getting, okay, is going to be this particular really huge volume. Okay? So, what occurs then is, oh, I should take it back. Sorry, I went to gallons first. I should have gone to kilograms. Sorry, my bad. 3.42 times 10 to the 5th kilograms. That's the actual value. 3.242. That's the mass, okay, that you're going to generate. So, with that then, okay, turns out 1 gallon is equal to 3.785 kilograms. All right, convert this from kilograms to gallons. Also, just to let you know, an average swimming pool is about a 20 by 40 foot pool is about 30,000 gallons. That's one pool. So what I want you guys to do, figure out how many gallons it is, and then figure out how many pools that would be to charge 1 Tesla. If the sub could stop it just for a minute, well, people do that problem. Okay, how did it work out? 3.42, 10 to the 5th kilograms from the problem before. 3.785 kilograms here is 1 gallon. You work that out and you find out that you should have 90,583 gallons. That's a lot of water. Then to get the pool, you go 90,583 gallons. And then you get 30,000 gallons is one pool. So you get about 3. It takes about 3 pools of water going over to get that to occur. Massive amount. All right, the rest of the time you guys are going to be doing this. We got a series of videos, a worksheet to work with to have you guys concentrate on what's occurring relative to energy and alternative energy sources. Huge issue within the United States and the world. I'm going to be back next week, take a look at these particular videos and that sort of stuff, and get ready to roll. See you guys.